Go.
ID number 4, one paper clip. 1, 2, 3, go.
A helicopter experiment, right? This is quite a lot of fun with paper. So in this case, here's the helicopter, and I have a video demonstration to show you what it looks like. But we looked at three different things. We looked at wing length, body length, and then the number of paper clips used. So wing length is this dimension here, body length, this dimension here, and then the number of paper clips was either 1 or 3. Okay, so what we did was we cut them out. So you should be able to hear this. If not, let me know. It's a very short video.
Go.
ID number 4, one paper clip. 1, 2, 3, go.
And the response that we were looking for was time. And there's all sorts of interesting things associated with this because there's lots of factors, lots of sources of variation which could skew our results. So first we have to decide when we're designing an experiment, what's the direction of goodness? In our case, since we know things fall at 9.81 meters per second squared, I decided that the direction of goodness in this case would be how long can we keep the helicopter in the air? You know, so that means the direction of goodness in this case is more time is better. Sometimes we're trying to minimize time for our response. Sometimes we're trying to hit a target. I went through, did a real quick mind map of sources of variation, and we looked at, for instance, inconsistencies associated with cutting, folding, drop height, or hold point. And in fact, there's other videos I have decided not to show you where we discuss, well, how do we determine the right drop height? How do we determine the hold point? Because with the helicopters, if you hold them underneath the wings, then it's going to interfere as you release. So that's why we decided we had to pinch from the top and let it drop. Also, too, lots of things going on here. For instance, measuring elapsed time. Since I was using my phone to video that, I decided I would use my computer to do the timing. Well, it turned out that I couldn't reliably start and stop an internet-based watch. Okay, so we had to just switch over and use a different stopwatch. Actually, somebody else's phone. It was much easier to use. The other thing was I had the back door open. It was a nice day. Realized, the first time we did it, we saw the helicopter go sideways. Like, oh, whoa, that's a problem. So we had to close the door. And it's these things you need to be aware of. Another thing was I thought I would save some time, so I rated my stash of paper clips, and I figured, well, I'll just put paper clips on all my different 8 models, and I'll save some time that way instead of having to change them all out. Well, I don't know how well you can see this, but I actually decided to see, are paper clips really the same weight? And as it turns out, they're not. I don't know how well you can see this, but excluding the ringer on the right, which are the 1 gram, the others ranged from 0.2 to 0.4 grams. Now, in an experiment with paper clips and helicopters, or do you think it matters if one paper clip weighs twice as much as the other? I think it does. I didn't try this, but so what I did was I ended up picking the same 3 that I used every time, and they were all 0.4 grams. So I removed some variation there. I think that's pretty important. So one of the things that I want to spend a little bit of time on is, because if I hadn't controlled that variation, I would have gotten results, and it either would have been muddy, not able to tell me anything, or they would have led me down the wrong path. So one of the things that you want to do, we say that planning your experiment is critical. Controlling variation is one, obviously. So here I just reproduced the mind map just so you can see this, but inconsistent cutting, what do we do about that? Well, let's make sure we're aware of it and really try to work on it. If we screw it up, then we may have to print another one out. Inconsistent folding, inconsistent hold point. And again, you may have to do some pre-experiments like we did to try to figure out the best way to hold it. How do you get that consistent drop height? We were using a ladder, right? No chairs, right? You don't stand on a chair. not doing this experiment. And I was fortunate enough that I was in a high enough area that it worked. I will tell you this, I've done these experiments very nicely on a mezzanine or in a stairwell. If you can drop and get height, the more height, the better, because there's all sorts of variability. So we want to try and minimize that. Okay, breezes in the air. If you see your helicopter going sideways, do something about it. Starting the timer. So using a stopwatch or a phone. And what we did was we figured out that the person dropping would say 1, 2, 3, go. And then stopping the timer, the person who was best able to timing was best able to tell when it landed. And of course, if you're doing it on a non-carpeted floor, you can actually hear the paperclip when it hits the ground. So that helps. And then you can see here the variation of the paperclip, which I picked 3 to use for all the experiments that were the same weight. So now let's talk for a minute about this. I don't know if you can, how well you guys can see this. If I need to, I will blow this up a bit. Okay, you can see my spreadsheet now?
Yes, we can.
Great, okay. So this is open source from ASQ. I happen to be an ASQ instructor as well, but different story. I found this to be the best of the simpler Excel spreadsheets that are available online. So as you can see here, right, there's some instructions here, not an awful lot, but over here, this is an interactive piece where I was able to put in my wing length, my body length, and the clips that I use. Now we're getting back to the helicopter experiments. So hopefully all the things I told you before are going to come into play here. Also notice factor A, B, and C. My low levels, 70 and 120 for wing and body, and then number of clips, 1 to 3. And you can see here, so this is, if you take a look, the numbers here, the 1 to 8, that would be from all low levels, then to all high levels. But in actuality, as I told you before, that we want to randomize it because we want to make sure there's not some other factor that is changing through the day. So we randomize the run order. In this case, we're doing it like this. So you can see here, so for this run, we would use low, low, low settings. Here are those factorial matrices that we were looking at before. So here is the AB interaction if it exists, wing and body length, wing and paper clips, body and paper clips, and then the possibility of all 3 of them together. So that's possible. Now, if you take a look at this, in some cases, I actually took a 3rd trial, but I didn't put it in here because they were semi-botched runs. But if you can see here, here's a little bit of that short-term variability. What we did was we dropped helicopters. We dropped, say, this low, low, low setting. We dropped it once, and then handed it up to the gentleman on the ladder, ran it again. So is there variability in how fast each one of these falls? Sure, because it depends on how we released it. Did he release exactly on go? Did I, who knows? Did I stop the watch as soon as it hit the ground? Or is this variability in the process itself? It's hard to say, but tell you what, rather than taking 1 reading, if you take 2, you can average them together and it's going to help. You can see here now, we've got some variability associated with most of these. Actually, with this run here, this one came out exactly the same. I said, woohoo, let's just move on. I didn't want to, tempt the fates with a 3rd run and see how much variability there was. But I mean, you can see here, you're talking about a 10th or, 0.15 seconds. It couldn't matter, especially when you're talking about a response that's this small. Remember, I said too that in this case, the direction of goodness that we decided on was higher. Longer time in the air is better. So that's what we're looking for. I mean, of course, if you were in a war zone in a helicopter, you might actually want shortest time, or you might target time if you're trying to reduce G-forces on people or whatever, right? So it really depends on what you're trying to do. And here's why you've got to think about these experiments. So now if you take a look at this might help just to reinforce what we're talking about here. And the reason why I like this was because it actually shows you the calculations. So here's the calculation for factor A, right? Here are the main effects, A, B, and C. Here are the interactions, and we get to see which ones are important. So here's how we calculate factor A. You can see here, if we go to factor B, you can see now it changes. What we're doing is, again, we're looking at the average response for the high settings the average response with low settings, and then subtracting them. So actually with factor B, we get a negative result. We'll talk about how to interpret that in a moment. Same thing with factor C. You can see, okay, that we get a sort of small result as well, right? When we change the number of paperclips from 1 to 3, it really only affects our time by 1/10 of a second. Actually, what's interesting that is interesting, really. Now, if we take a look at the interactions, again, you can see these, and that's why I threw in those slides about interactions. I thought that was sort of important. Calculating interactions gets a little bit more complicated, so I prefer to let software do it. But in this case, you can see we've got somewhat of a strong interaction here. Okay, if you take a look at this, this is A, which is the wing length, the low and the high settings, and then the blue is body length low or short versus body length tall, long. And as you can see here, if we're looking at this, given that we've got a long body length, when we go to longer wings, it ends up being less time, at least in our experiment. Okay. Now that could be the experiment. I mean, you generally would prefer to do more than one to validate the effects of this, but it's not always possible to, especially if it's a destructive test that you're doing. You might not be able to replicate it, or it might be too expensive. You might not be able to get time on the equipment. Whatever the reason is, there could be lots of reasons for it. Okay, again, we're looking at the interaction between wing length and paper clips, and for a large number of paper clips, the 3 paper clips rather, as you can see, when the wing length goes from low to high, we actually get a reduction in the time that it takes, which might be counterintuitive, right? You might think a longer wing gives you more lift, and it sort of does. As you can see here, all things being equal, now let's go back and interpret these. For all things being equal, as you go from the low level of factor A, wing length, to the high level, you find an average increase of 0.087 seconds, it by itself. But take a look at these interactions. Given this wing length, as you can see, we've got this negative interaction here, which is much larger than the effect due to A. So that's why interactions become important. You might want to pay attention to them. That's the reason why sometimes you don't get the results that you expect, because people ignore interactions. Anyway, continuing back to interactions, if you take a look at body length, the way to interpret this is, as we go from a short body length to a long body length, then the average time in the air reduces by almost half a second, 0.4 seconds. Okay. Likewise, possibly counterintuitively, to interpret this, as we go from 1 paperclip to 3 paperclips, we actually end up with an average increase in the air time of 0.1 seconds. Okay, so this by itself, if you were just to look at A, B, and C, you'd say, okay, well, clearly we want to have long wings and 3 paperclips. And we would prefer to have a short body here, right? Because remember, as we go from a short body length to a longer one, the time in the air is reduced by 0.4 seconds. I don't know why. Maybe the aerospace types in the room would know this stuff, but I don't know why it is. I'm just telling you that is what happened in this experiment. And that's why it would always be good to run a confirming experiment to make sure that's still the case. When we start to look at the interactions, you can see here now that there is this difference in response of 0.65 seconds. Okay, so let's see if we can figure that out. I don't think I can I move this? Okay. So there, I can move it so it's out of the way at least. So as you can see, now remember with the interaction, I didn't really go through the multiplication, but you take the -1 times -1, that becomes a +1. We can go back through that if you want, but as you can see here, for a long body, as we go from a short wing to a long wing, our values go up. And likewise, then, if we look at the long body, as we go from a short wing to a long wing, the times go down. So why it is that long body, long wing has the lowest effect, again, I can't explain that, right? It's almost like all the aerodynamics of paper helicopters is a black box, and I'm just saying, well, if I change this setting, here's the effect of it. Okay, so you can see in this case, just by looking at the magnitude of these bars, and I'm not saying any of these are good or bad. Again, it really depends on what you're trying to do. But what we could do is try to figure out the best settings for it. And in fact, just on the charts, you can see if I'm trying to maximize things, if you look at the AB interaction, sorry, I had 2.78. Okay, that's the highest number I've seen so far. Just looking at these numbers, so 2.78. So we would want to make sure, and there is no three-way interaction that they can display. So anyway, so what we can do is use a combination of these charts and graphs to tell us what the best settings are for a given target. Again, if we're just trying to maximize it, it's easy. We grab the max values and then go back and try confirming runs to see if that's the case. Right, so after the main experiment, we get the results, and then let's validate those results. Right, you don't have to run the whole experiment again, unless you actually try to run with this set of combinations, and then you get a different result. You get a different result than you expected, then you may need to run your experiment again. I mean, if you take a look, actually, going back to this experiment right here, it says that large wing length, short body length, and one paperclip gave us, right? Yeah, gave us the most time. Right? Whoop. No, this is the one. Yeah. So long wing, short body, and one clip gave us almost 3 seconds here. So we might want to go back and validate that now that we understand that there are interactions. What would be neat is if you actually did run the whole experiment again, you'd get to see if there was any variability associated with picking your drop height, being able to start and stop your timer. And again, you may have to experiment with some of the stuff ahead of time. So I could continue to talk about things, but Dr. Ryan, I've actually hit the end of my presentation unless we want to go more. We've got some time. Are there any questions, or do you have some things that you want to add to this?
You know what, I think it would be a good idea to open it up for student questions at this point.
Okay, great.
I actually do have a question, if you don't mind. In the beginning of your presentation, you were talking about the experiment we did last semester with the catapult. You talked about the rubber band introduction and how that can wear over time. You mentioned that as environmental, but my question is, why is, and with respect to Six Sigma, why wouldn't that be considered material and like material fatigue?
Well, it could be material. I mean, technically it is, right? I mean, rubber band is the material that you're using. However, unless you're actually specifying the properties of that rubber band and purchasing to that spec, then it's what we would call noise. Because, after all, if you're buying rubber bands at Staples in any given bag, I'm sure they have varying properties of elasticity, elongation, that sort of thing. So Mother Nature or a noise variable is something that we don't currently control. If we decided rubber bands were critical, then we could put out a spec and pay 10 times more to get them to our design. And then that would be a material issue. So good question, really good. That's it. I mean, I'm happy to go into it more. Okay, Dr. Ryan mentioned during the chat that Excel does have some very good statistical tools in the data analysis package.
Yeah, and I'll just say that data analysis package is free. And if it's not on your Excel already, you can just add it in through the menu bar. And there's a lot of other softwares out there that the Temple community has access to. Jump is a good statistical analysis software package. And the reason I wanted to say that is because it's important that when you report your results that you talk about you know, the statistical significance. So if we look at what's on the screen right now, you know, if you have a set of experimental results in which, you know, changing one variable increases your result, improves your result by, you know, 0.1%, is that meaningful? Maybe, maybe not. And that's why, you know, the statistical analysis, looking at the p-value, et cetera, would be useful.
Absolutely. I mean, you get so much more with software. With software, you would not only determine which effects and interactions are significant based on your p-values, you would also get a regression equation out of it that you could use for prediction, a prediction equation.
Yeah.
And I didn't get into that now because, oh wait, had I, we'd be going until 12:30. You know, how you derive and how you do that. So I ignored that, but I was laying in bed last night thinking to myself, I should really mention that regression equation, that it exists and there's a way to calculate it. But I'll leave that for you guys to do. So, questions? Other questions? Thoughts?
I do have one question for you, Manny, because I'm looking at these results and I find it curious that as you adjust factor A from low to high, you get this positive impact on time. When you adjust factor B, you get this very negative impact. But when you take A and B together, it's even more negative. And I would have expected, if you've taken a factor that is having a positive impact and a factor having a negative impact, taking them together would land you somewhere in the middle. But the results that you found were that A and B together actually make an even lower time difference, right? So do you think that's just an artifact of this experiment, or do you think that, is this something that you see very often?
I don't necessarily see it very often, but it very well could be beer and cold pills. You know, you have the effect one way, but then you add more of something else and it changes it significantly. Don't know the physics behind it, but I will say that what it did was the A/B factor, it looked at the minuses and then it looked at the pluses. And so that's why you can't just go into stuff blindly and say, okay, well, I've got 3 factors and I want to do 2 arbitrary levels and I'm not even going to think about it. You need to understand a little something about the system or the principles. It would be good to have a hypothesis about what you do expect to see so that you can then understand or help to get closer to, did I screw this experiment up? Which is entirely possible. I was not completely comfortable with it. Or is this really the way this goes? But you can take a look and parse through it. You can go back to the original matrix and thereby try to figure out the best combination of results. This template doesn't give you that. That'd be the regression equation. Or I know in Minitab, you can have what they call a response optimizer. Are you trying to hit a minimum, a low, or a target value? And it will tell you the best settings to use.